All right. Thank you, everybody. Hopefully no technical difficulties. And I know we're running a little bit late and we have lunch coming up. So I'll go through this pretty quickly, but I want to just make sure to say thank you to everybody for coming and for inviting me to give these series of talks. So there's a series of 6 talks of more of the education side before we talk a little bit more on the details on some of the technical. So these next 6 presentations, 3 today and 3 tomorrow, are kind of general education and focusing a bit, since there was going to be a mixed audience, some from this institute, from the hospital. So some are, I'll apologize, some might be basic for those of you that are very familiar with radiation oncology. And then for those on the physics side, more on the accelerators, maybe that might be a little too basic for you when we go over through some of the accelerators. But hopefully there's something of interest and education for everybody. This first talk is really going to be a primer on the basics of accelerators and some basic physics for proton therapy. But again, since there was a general audience, I wanted to start out with doing a little bit of the kind of a history of particle therapy. And a lot of times I'll refer to it as particle therapy because it has been maybe mentioned a little bit of interest in maybe doing carbon therapy here, maybe not immediately, but in the near future, or maybe even doing helium or some other particle that may be of interest. So usually when I say particle therapy, I'm meaning mainly for this audience protons, but it's also true for if you were to do a helium or a carbon beam. So I'll go through a brief history of particle therapy, some of the basic rationale, mainly for proton therapy there, go through some of the accelerators, some of the basic information for the accelerators, and then a little bit on the introduction to some of the basic physics to think about. And then on the different series of lectures, we go into in-depth a little bit more on the radiation safety, measurements, et cetera, treatment planning, and so forth. So now a very brief history, just so everybody can be at the same page. So over 100 years ago, Sir William Bragg published his discovery for the proton Bragg peak. And that's what we actually take advantage of when we're treating patients with proton or particle therapy. Now, also in 1946, it was proposed by Robert Wilson to use proton therapy and particularly take advantage of this Bragg peak for cancer treatments. So the concept has been around a really long time. There was actually, again, this is already 70 years ago, protons were used to treat some cancer patients in a laboratory setting. And the main thing about here in initial proton therapy and particle therapies, they actually all took place in what we would consider physics labs. So maybe at the Synchrotron Institute you have here or other places, and not necessarily in hospital settings. So for instance, one of the largest programs that ran from 1960 to 2002, so over 40 years, was from the Harvard cyclotron facility. Again, this was in a university setting at a physics lab, not at a hospital, but treated many, many patients with proton therapy. And then also in the US, in the Berkeley National Lab, so the other side of the coast, from the east coast of the United States to the west coast of the United States, treated with heavier particles. This included carbon, but it also included neon beams, helium beams, and everything kind of in between there. So again, since 1975, so almost 50 years ago, we're actually treating with particle therapy. And again, this was in a lab, more of a lab setting, a physics lab setting, than in a hospital type setting. The first actual hospital-based proton facility was the Loma Linda Center. This is again in California on the west coast of the United States. And this actually is maybe a little misleading to say it was a hospital setting. It was in a clinic setting, so it's more of a standalone that was in a nearby hospital. But as some have mentioned earlier, you had to build a whole new building for it, and you needed a lot of space, so it's kind of off to the side and not really integrated in with everything else. And maybe talk a little bit about carbon therapy. The actual first carbon dedicated facility for patient care was done in Japan in 1994. And so again, this is almost 30 years ago. And in that facility, they're still treating today. Right now, as it was mentioned earlier in 2023, I think the number you had up was about 134 centers. I pulled a number about 110. I mean, there's a lot of proton centers throughout the world right now, and depending how you want to count different ones, and about 15 carbon therapy centers in operation, actually treating patients today. So this right now is just an overall map kind of showing the blue ones are the carbon centers and the red ones are the proton centers. And the proton centers kind of vary all the way from maybe being 4 rooms in a facility, 4 tumor rooms, to single rooms. So originally, when proton was first starting out, there were larger centers, maybe 3 gantries or 4 gantries. And then as the technology evolved and more places wanted to open and couldn't build such large centers, more of these 2 rooms and now a lot of 1-room solutions similar to what's here in Bangkok. But just kind of show overall how many centers there are. And you can see I don't know if it shows up, maybe not. Won't mess with the technology, but there's the one in Bangkok here. Now, number of patients that have been treated. So by the end of 2023, so at the end of last year, over 350,000 patients have actually been treated with proton therapy and over 50,000 patients with carbon ion therapies. So again, over 400,000 patients have had this type of treatment, particle type treatments, and overall very positive outcomes. Here's just a kind of, again, just to give a broad overview for those that aren't that familiar of kind of the indications. And this is basically broke up worldwide, just carbon ions and protons. And then what's happening in Europe, in Asia, and apologies, this one was supposed to be America, but it got messed up. But you kind of see that there's actually a lot of difference between Asian proton centers and European proton centers, let's say. You see a lot of GU, mainly prostates, where there's not that large of an indication for treating with prostates in Europe. But both have very large for other indications that you kind of see the head and neck. And in one of the other talks, I go into a little bit more about head and neck and why that one's important. And of course, pediatrics. Okay, so that was just a broad overview to get kind of familiar of how many places there are around the world, what kind of patients are being treated, and we had some of those talks a little bit earlier. So now I'm going to go a little more into the rationale and current status of proton therapies. From overview, now talking why you'd want to do proton therapy, kind of the motivation. Again, this one, so now I'm going to focus in the United States because that's, my background, so I know that much better. So currently there's over 2 million new cancers are diagnosed per year in the United States. Population of the United States is about 350 million. Thailand, I believe, is about 110 million. So the number here is going to be very comparable, and that was discussed earlier today. And of that, more than half actually receive radiation therapy, most of that being some sort of external beam radiation therapy. And 75% of those that are actually treated are treated more with a curative intent. Some are treated for palliative, for pain management, etc. But radiation is actually used, mainly to cure cancer. That's why we're doing the radiation therapy. And again, most common indications: prostate, breast, lung, and brain. In the United States, there's over 2,700 radiation therapy centers. So that's mainly photon therapies. It could be from a place that has maybe 1 LINAC treating, that maybe centers like mine that have, dozens of LINACs. Yeah. So as we were talking earlier in the break about radiation therapy and fractionation and such. So again, a little motivation. You want to give a large amount of radiation to the tumor. So you can think of the radiation as the medicine. You want to kill the tumor. And the more you can give to the tumor, the more likely it will die in general. And therefore, you're longer survivor, more likely that you're going to cure the patient. But kind of again, given that higher dose, you have normal structures around. So a lot of times you would do therapies that would break it up every single day. The way I kind of think about it, when you take an antibiotic, you take one every day or two a day, every day for a long period of time. So you get, and make sure you kill all the bacteria in the body that's giving you a sickness. Same thing with radiation therapy. Particularly when you can't spare the normal tissues that well, you want to give a little bit to the tumor every day, kind of give your normal tissues chance to repair themselves, but get that tumor every day a little bit more till you can totally eradicate it. And again, the higher dose to the tumor, usually that was more fractions. And as was discussed earlier, every time you do, every day you give a treatment, that's a charge for the patient, it costs more money. And usually the higher dose you give to that tumor, well, there's normal tissues all around there. So the higher dose ends up going to the normal tissues, say your spinal cord or to the normal part of your brain, et cetera. And that leads to toxicities, either acute, get really bad symptoms immediately, or long-term. And kind of the long-terms are hard to really judge and get a good handle on because it can occur so many years later. Maybe 6 months later, maybe 2 years, maybe 5 years later. So this is one of the motivations for proton beam therapy or particles in general. So what do the patients need in general? And as kind of mentioned before, we want a long, healthy life free of cancer. That's where we want to get to. But you also want the long, healthy life free of adverse events. So if you kill the tumor but leave the patient in a very bad state and their quality of life isn't so good, that's not necessarily the best thing. And it's physical and emotional things to be considered above. And also the financial aspects. If it's very expensive, well, that leaves a big burden on the patients. So again, what is the goal? The goal is to prevent the growth of the tumor or reduce the tumor size so that then you could do surgery very well. Reduce your toxicity, both the early and late effects. And as radiation has advanced, we've been being able to improve the technology so we can improve these goals of being able to cure more patients and less side effects. Back again, since radiation has been used back in the early 1900s, so over 120 years, we've improved the technology all the way, and we discussed a little bit about IMRT and VMAT. All the way to now where we do intensity modulated particle therapy. So this is again, motivation why proton therapy. This is a common slide that was shown earlier also. This is what we call cranial spinal irradiation. And maybe, I don't guess that the laser is not showing up. That's okay. So on the left of this is a pediatric patient. The point is on these type of very large volumes where we're treating, well, the patient would get a lot of radiation to their normal tissues, which is not good, particularly for pediatric patients. So how do we reduce that dose to the normal tissues? And some things terminology we use in radiation therapy, a GTV is usually what we call the gross tumor volume. So this is the thing you can see on your imaging, either your CT imaging or your MR imaging. Your CTV, clinical target volume. So as we all know, the horrible thing about cancer is it also spreads, and it spreads microscopically. So 1 or 2 cells getting away from that tumor spreading out is not good, at least to metastasis. So there's this volume where the physician usually contours to say this is where they think there may have been some little bit of spread that's not actually showing up in the imaging, but is probably there. And what we want to do is give a lot of high dose to those that area where we believe there's a tumor, and ideally no dose anywhere else. But there's always uncertainty in overall when we deliver the radiation, how the patient is actually set up. So when we talk about these things, we're usually thinking of things in the terms of millimeters. So if you think of 1 or 2 millimeters, but then put that in the human body and saying we're trying to be as precise to deliver to 1 or 2 millimeters, there's always some uncertainty. So we have to take that into account too, because the worst thing is to be able to get really high and effective radiation, but then end up missing part of that tumor that then grows back. So we want to make sure we take care of that. This is just to give an idea, some concepts of when we're talking about these normal tissues, how sensitive things are. So for fertility, that's one that's kind of easy to measure. For males in the testes, a few, and this unit that we're going to use is gray. And I talk about that a little bit more. But a few gray, can lead to sterilization there. And in women, maybe 10 to 20 gray could lead to sterilization. Now, to put this in context, when we usually want to, let's say, kill a tumor, the normal doses, and every tumor is a little bit different depending on the size, location, and its histology, et cetera. But we usually do things maybe, let's say, 50 or 60 gray. So we want to give 50 or 60 of these units of radiation measurements to the tumor. But you see, some things are very sensitive. So cardiovascular, there's been many publications kind of showing that you can have an increase in cardiac adverse events even if you give maybe an average of 3 gray to your heart. And the vasculature may be leading to stroke or heart disease, maybe up to 4 gray could be sensitive. That gives an increase. Of course, the eyes are very sensitive. So these are some of the sensitive things that we have to be careful of when we're giving this radiation. And here's just a little bit again for breast cancer, just to show that this low dose matters. The reason I'm concentrating a little bit on all these low doses is that's where proton therapy, particle therapy in general, proton therapy kind of has its main benefit. In proton therapy, we generally give the same amount of radiation to the tumor that we do for photon therapy, on average. But the benefit is being able to reduce the radiation to all that normal tissue around you. And here showing for breast cancer, as you can imagine, breast cancer, if you're giving a radiation that's not very directed, you could give some to the heart and to the lungs nearby. And this is just showing kind of the mean dose to the heart and kind of the percent risk for a coronary event later in life. So you see that even when you get to these really low doses, 2, 3, 4 gray, again, remember, we're usually treating something maybe 40, 50 gray. So we're talking about 10% of the treatment dose. That actually matters. So again, the dose reduction to the normal tissue is very important. So you could just maybe something that's very easy to understand, the brain. You don't want to give any extra radiation to the brain. So you want to increase your tumor control. So the green line there is supposed to represent, we usually call this an S curve because it looks a little bit like an S. So the more radiation, this unit of measurement, the gray is a joule per kilogram, the more you can give that kind of energy to that tumor to eradicate it, the better probability you have of killing the tumor, of getting your disease control. But then you see, the more you give there, the more you're going to give to your normal tissues around. And in a general sense, the normal tissues are sometimes a little less sensitive to the radiation than the tumor. The thought behind there is the tumor, essentially something is wrong with it, particularly given its repair mechanisms. So it's a little more sensitive to radiation than your normal tissue. But you see, as you give more radiation to your tumor, your normal tissue is going to get more radiation, and the probability of something bad happening increases. So I actually worked at St. Jude Children's Research Hospital. So here we only do pediatric patients. I worked there for about 6 years, focusing on pediatric proton therapy. And as you see, 85% of pediatric cancer patients are cured. So that's a very large cure rate. But if you're giving using radiation, giving this, their pediatrics, given the long life that you're going to expect for curing the pediatric patient, the more likely some secondary type or late effects is going to happen. So that's where proton therapy can be quite advantageous to increasing the quality of life, particularly when we're talking now 5 years or 10 years or 30 years later. So what we want to be able to do is reduce the dose to normal tissues, increase that conformality, how well we can actually conform the radiation to the tumor, again, so we spare the normal tissue. And here's just an example there. We showed examples earlier, but you could, just by visually, you could kind of see this in MR, you can kind of see something doesn't quite look right. There's your tumor. So this was a young adult, a pediatric patient. I believe she was 15 years old when she first presented, but she used to run marathons and such for high school in track and field, and gradually she became slower and painful to run, and because she had this massive tumor. And here's just showing a quick example again, motivating proton therapy before we go into kind of some of the details of why we want to do this. Just looking at this, you don't have to be, that educated in necessarily what we're looking at, but the red is high radiation dose. The green is moderate, blue is low. And you can see here, the one on the right is the proton therapy, the one on the left is the conventional, what we call, advanced IMRT or VMAT, these advanced therapies. You can still just see all the radiation that's going to go. In this particular one, like I said, this is a female track and field athlete. On the right there, the arrow is pointing to the ovary. So normally in a normal one, she would have had that much radiation to both ovaries and would not have been fertile or be able to have children later in life. But here, and one thing that some would actually do a kind of transplant ovaries. So you had to do a surgery, move them out of the way of the radiation, and then afterwards, kind of put them back. So that's surgeries, and there's always possibilities of things with surgeries. Here you can see we totally spared one of the ovaries, so therefore there was no need for having that surgeries or going through that extra expense. Here's another example. Here, there's actually two sites, but I'm concentrating on one. And for those, again, when we talk about this gray, this joule per kilogram, in this one, the red part right there, we're going to 63 gray. And what I'm showing here, again, since this was going to be more mixed audience, not necessarily radiation specific. So 1 gray, on average, you could think of that about 100 CT scans. Maybe it's 50, depending how you're looking at this, or about 1,000 chest x-rays. So that's 1 gray. So what it's showing here, where you see that blue, that's a couple grays there. So you can see traditional x-ray therapy, you get all that radiation. Now, is 2 or 3 gray here? Can we actually measure acutely what's going to happen? No, but particularly as was shown earlier, we're kind of now saying, proton therapy, maybe even anybody under age of, for sure, 21, or as was shown, maybe under age of 36, maybe under age of 45, or life expectancy, you cure this, maybe live another, let's say you're 40 years, 50 years old, you may still live another 30, 40 years. So what is this radiation, all these extra doses doing to the rest of your body? So just an example to kind of help put in context of why we want to do proton or particle therapy. Now, again, some of the benefits that it was already talked about a little bit, but this was actually a quite old study, a European study, but I thought it was very relevant. So the radiation, on general, the radiation therapies that we saw, the proton machines are larger, it's more expensive as one would expect. And here saying about twice as expensive as a normal photon therapy. And this was for pediatric medulloblastoma, and I'll show one later for an adult patient. But the adverse events, so now when you take the whole cost of caring for that patient long term, you can see there's quite a bit of savings. So sometimes people really look at this and say, oh, the proton therapy, particle therapy is really expensive. And it kind of depends how are you counting. It might be really expensive, right that day, but when you take the long-term approach, particularly as cancers are increasing and there's a trend a little bit younger to be getting cancers, but life expectancy is still a lot longer. There's a lot of benefits for proton therapy that are hard to quantify just immediately. Here's one more looking at acute effects here. And this is for oropharyngeal or head and neck, so cancer kind of in the head and neck area. And this one particularly was looking at maybe feeding tubes. So again, when you have the cancer in this area, you have a lot of that very sensitive normal tissues, basically eat and breathe through here. And a lot of times as you're going through this therapy, partway through the patient, you need to have feeding tubes put in, et cetera. And a lot of extra care associated with to cure them using radiation, they need all this extra care. But with proton therapy, it's been shown, and here was a study from 10 years ago already, that the cost, and this is the acute, just a short-term cost, but there was actually a benefit with proton therapy because you had less of these side effects, less of these interventions. And again, that was looking at the short term, and you can imagine if you include everything else in the long term. Okay, so that was the quick introduction to and some motivation for proton therapy. And this lecture was supposed to be mainly looking at some of the accelerators and maybe more on that physics side. So now for those that are more familiar with that aspects, maybe this might be not as interesting to you, or hopefully maybe you'll still learn something. But first, I want to talk a little bit about scale before we get into some of the details. So this is a traditional radiation, a photon therapy machine. So when we say photon therapy, though, what's actually you use an electron, and you do an electron accelerator, and it hits the target, create photons, and that goes through the body to treat the cancer. But the scale I like to put here, you can see the purple person there. That's so you can think of these as a scale on a person. They fit in a room. You can kind of manage. You can see it. You can kind of see it all in one take. Now, when we talk about proton therapy, and this is on the left there is a variant machine similar to the one that's here in Bangkok, and on the right is an IBA machine. So now we're a slightly different scale. So there's the accelerator on the left, and there's the arrow there's pointing to a person. On my screen, it's very small. Maybe up there, it's a little bit bigger. And then on the next one is a gantry. So that was kind of shown earlier too, but you can kind of see the person there on the bottom left corner. And then here's in the accelerator, and this is it's an IBA machine, but it would be similar for the actual variant machine that's installed here. The accelerator and then the energy selection system. And I'll talk about these components in detail in a little bit. But these systems are big, right? You can't really, I wouldn't really say they're on the human scale. They take up multiple rooms, so a little bit bigger than that, maybe the scale of a house or a building. Touch on carbon just a little bit. So carbon systems in principle are the same as a proton system. They're just bigger. So proton, when we say proton therapy, we're actually talking about using the nucleus of a hydrogen, so one proton. When we say carbon, what we're talking about is using the nucleus of a carbon atom. So you strip off the electrons, so there's 6 protons and 6 neutrons, so 12. So it's just bigger. The accelerator is bigger, the gantries are bigger, etc. But again, you see the little purple person there, so a lot larger. Kind of no longer on the human scale. And in the second lecture, I'm going to talk about radiation shielding, about the center we're putting in. I'll talk about how we did the radiation shielding calculations for that. It's a carbon accelerator that we're also going to use for protons that I'll be talking about. All right, so that's kind of give you a sense of the scale. So what do we use in proton therapy? I'm not going to talk about some of the more exotic things that people have proposed. So I'm going to use, the mainstay, cyclotrons and synchrotrons. When I talk about the vendors, I think, I'm not too sure which lecture that is. That might be the 5th or 6th lecture. I'll talk about some of the ones that are using some other accelerators like Linux, etc. But primarily, most are either a cyclotron or a synchrotron. So first, these are just basic definitions. So a cyclotron, that's let's say one fairly large accelerator, kind of just think of it one big hunk of metal. And what this does is the ion, so it has to be charged, so the proton or a carbon atom goes around in a spiral, and it gets a kick of energy every time, and it's a fixed magnetic field with a fixed acceleration radio frequency, and it gets more and more energy as it spirals out of this system, and then it comes out, and that's what you use to treat. The systems that are here, and the one that's actually here in Bangkok is the variant system. It uses an isochronous cyclotron. So, and I'll show this in a bit, but cyclotrons, when you first think of them, you think of the traditional thing. Those are non-relativistic. Everything when we treat with proton therapy is a relativistic particle. So when we talk about 230 MeV, that's meaning that's the kinetic energy of that proton. that means it's going roughly 60 to maybe up to 70% the speed of light. So you're definitely in the relativistic. So, the mathematics is a little bit different. But the isochronous, what this means, it has to maintain the constant RF, so that the RF is your acceleration, the radio frequency, the thing that's giving the kick, giving it more and more energy. So that thing is a constant. It means a constant, and so that doesn't change. And the magnetic field is also static; it's constant in time. So the particle goes around and around and around, kind of spiraling out and gets to relativistic energy, then comes out, and that's what you use eventually to treat the patient. There's a different kind of a cyclotron, a synchrocyclotron. So now most of the vendors that do if you're to purchase a cyclotron, let's say from the new IBA systems or Mevion system or such, they use a synchrocyclotron. Advantage of these, most of these are first, they're going to be superconducting. Second, they're able to be a little more compact. And what this has is the accelerating frequency is actually changing in time, getting a little bit faster and faster. The magnetic field is still static. That's constant in time. So the way you think of these are a little bit different. One's kind of a continuous beam and one more still has pulses. And then the last one in this is the synchrotron. So all current carbon facilities are synchrotron based, and the manufacturers, the one that collaboration you're having with one of the China companies does a synchrotron. Hitachi, one of proton and car manufacturers, they use a synchrotron. And what that is, the magnetic field and the radio frequency, the accelerator, are both changing in time together synchronously in the synchrotron. But there, the thing that's fixed is that the beam actually goes in a fixed orbit. So it's a ring of a fixed orbit, and the magnetic field and the frequency is actually changing, but the particles keep going around the same orbit. And that might make a little more sense when I actually show one. So first we're going to talk a little bit about synchrotrons, and then I'll talk about the cyclotrons. So the synchrotron, we already kind of described it, and this is a ring. This is a Hitachi system. The other advantage of the synchrotron, and an advantage of a synchrotron over a cyclotron system for medical use, for radiation therapy, is with the synchrotron, you can select which energy you want from the accelerator. Whereas a cyclotron, what comes out is a fixed energy, and then you have to do different things, which we'll talk about in a bit. So that's an advantage of the synchrotron. So here's just a basic picture. So there's a large synchrotron here in Thailand. What I'm showing here is a synchrotron at Indiana University. I'm showing that because that's where I went to do my graduate work. So I did some of my thesis work on this machine. So I'm just showing it since I'm giving the talk here. I figured show something that I actually worked on. So this is a basic synchrotron. So the protons come out at 200 MeV. We sometimes say per nucleon when we talk about ion therapy. So that's a cyclotron, and you see it has 4 of these big bending magnets, 4 of those dipoles. It has an injector. So the system that some of you went to go see in China would look very similar to this. There's a source, LINAC to inject it in. We'll talk about that more a bit, and an extraction. But synchrotrons are used for many things. I also put this one up here. This is from Los Alamos National Lab in the United States, because that's also why I did some work on this. Actually, the tube, the black thing down on the bottom, those inductors there, that's actually what some of my thesis work was on. But anyways, this is a synchrotron. This one is used primarily to store protons and then used for different purposes. It was approximately 800 MeV. So synchrotrons are used for many different purposes. Again, mainly for nuclear and high energy physics. So here's it was mentioned earlier about CERN, some of the collaborations with CERN. So this is the Large Hadron Collider. So it goes up to 6.5 tera electron volts. We usually talk about mega electron volts. So this is obviously very huge, big ring. But again, this is technology that's used for many different purposes, many high energy and nuclear physics purposes. For therapy, here's a basic layout for synchrotron systems. So you have your source, which we'll talk about in a bit, and your injector. That goes, so these are components that you need. Every single synchrotron-based facility is going to have some version of each of these components. So first you start with your source. Again, I don't have the laser pointer, so that box in the back corner on the left-hand side, that's the source. Then you're going to have this straight thing is called the injector. So depending on which system you use, you'll have different energies for these injectors. Then you go into the synchrotron itself, which is the accelerator. And here with the synchrotron, you pull out the energy you want, you go down your beam line, and then you go to your treatment rooms. So your treatment rooms could be gantry based, maybe you have a fixed beam room, etc. But this is the general layout for every synchrotron therapy system there is, whether it's proton or carbon or anything else. This is the layout that you're going to have. In a synchrotron system, as I said, there's a lot of components, and interestingly enough, this first component, meaning your source and the LINAC, this injector that goes into the synchrotron, sometimes is let's say could be as or maybe more expensive than the synchrotron itself. So it's relatively hard to get a lot of protons from your hydrogen source when there's very low energy, meaning they're basically just kind of floating there, and get that first acceleration. It's kind of hard to get that efficiently. This actually is the demonstration here is actually for an ion therapy. You can see there's a source for carbon, oxygen, and there's also a source for alpha particles, helium, and proton. But they all have the same thing. So you have to first get that source. You got to strip the electrons off of let's say the hydrogen atom, and that's just floating. Now you got to kind of accelerate all these kind of together and focus them a bit. And that's what all these are for. So you can kind of get the energy you want, get them focused. And then in order to inject into a synchrotron, you can't just inject them at like zero energy. They need some momentum in order for them to be injected and start their acceleration around this ring. So for protons, some systems have, this is a totally different, this is for carbon, but for protons, first you'd have what we call the initial stage of the accelerator. Maybe it goes up to 3.5 mega electron volts. And then you could use that to inject straight into the synchrotron. Or you could have an additional kind of a RFQ, radio frequency quadrupole LINAC, that accelerates maybe to a little bit high energy, for example, 7 mega electron volts, and then goes into synchrotron. It's important to kind of talk about this and understand when you're first thinking about building, if you're going to go synchrotron, and spending a little bit of time, because the collaboration that's here is with a center that may be putting in a synchrotron type system. So the energy that you inject into your synchrotron, that initial energy, has a lot of influence downstream. The more particles you can inject at the higher energy, there's this thing called your emittance and your acceptance. So your LINAC here is going to emit something, and then your accelerator, your synchrotron, has to accept something. And these two things have to be matched up as well as possible, so you can get the most particles into that synchrotron. The more particles you have in the synchrotron that then you can accelerate, the more you could use to treat the patient, which means the amount of time it takes to treat the patient is less. And the more time a patient spends at table one, the more time one patient spends at table is the less time another patient can be treated. And also the more time that the patient is on the table, laying there waiting to be treated and getting their treatment, the more likely they are maybe to move a little bit. Remember, we talked about trying to be precise down to 1, 2, 3 millimeters. So when you think of your human body and just laying there and want to be precise to a few millimeters, and now you're laying there for 3, maybe 30 minutes while the radiation is being delivered, as you can decrease that, the more precise it could be. So even though this is we talk about low energies here, 3 MeV, maybe 7 MeV, this is a real critical component to the whole system if you're doing a synchrotron-based system. This is just a picture of an RFQ. When I said these parts, and I'll go to the next one because it's a little bit prettier of a picture. But I say these things are sometimes more expensive than the synchrotron itself because these are very highly machined instruments. The synchrotron you can tune the magnets, you can tune everything else, but this LINAC, it has to be machined very precisely because it's very hard to tune it afterwards. So the LINAC, that first component for a synchrotron system, is a key component and actually one of the weakest links if it's not done correctly within the whole therapy unit. Here's just a picture of one kind of installed. The one on the left is a proton LINAC. The one on the right is a carbon LINAC. And so these are all also not necessarily small things. You know, these are fairly long, kind of massive devices that are all their power supplies, etc. Again, here's back to the synchrotron system. So for clinical proton synchrotrons, the key thing is you're able to extract variable energies. This is during the installation process. So synchrotron, it has some advantages over cyclotron. One disadvantage is physically it's bigger. Yes, to point here. Okay. So just some, again, since there is some interest, hopefully here in Bangkok or in Thailand in general, hopefully soon you guys will also be able to do, a carbon facility. But here's just some carbon facilities throughout. Toshiba is a manufacturer. MedAustron was mentioned again. There's one, with collaboration with CERN, Mitsubishi and Hitachi, although Hitachi now kind of owns all the Mitsubishi centers. And again, just an example that we showed earlier. So for carbon centers, they're much larger. This is the one at MedAustron. Okay, so now let's talk a little bit more in detail about that injector system. I talked about some, but I want to show, and again, normally this is, everybody kind of overlooks this part. You always think of, you saw that big synchrotron accelerator and that gets all the attention, but this is where it starts. And if this isn't done correctly, as I said, there's the emittance and acceptance. If this part isn't well-tuned properly to match the synchrotron acceptance, then you're not gonna get as many particles into that synchrotron, and then everything downstream from there just isn't as efficient. So it's important to understand this process and make sure that the combination of the injector and the synchrotron work well. But again, you have for protons, you use a hydrogen gas that goes into what we call in the source. This is use a microwave to kind of start to accelerate. And then you have your LINAC. This is all in vacuum to kind of go through and accelerate. In this schematic here, this one goes up to 3.5 MeV. Then there'd be an RFQ LINAC at the end if you want to go further. So again, important just to understand how this part works. So this is a schematic of a 4-quadrupole synchrotron. So this is kind of a cartoon of, let's say, the Hitachi system. The system you guys look at is similar. I think it has 7 quadrupoles, if I'm not mistaken. But anyways, so the injector we just saw kind of injects into this part right here, into this electrostatic injection system here. So again, just like anything else, these particles are coming in from one accelerator, and now it has to come in and meet the other accelerator, and they have to be well tuned together in order to get the most efficient system to treat the patient. So what gets a lot of attention are the red thing here, the big quadrupoles. Then the dipoles, and then the green there are some of the quadrupoles to be able to focus the beam. The more you compact a synchrotron, so the advantage, the more you compact it, the less physical space it takes up. The less physical space that takes up, the more space you have for other things, for treatment rooms, etc., and the lower cost it makes for the building. A disadvantage when you start to shrink it, one, the amount of particles it's able to actually hold, it decreases if you're not very careful. And second is these dipoles, you have to really start making them so that they can also act as a quadrupole. And what that means is as the beams are going through, as they're bending, you can kind of think of it as a mirror. As it's bending on the dipole, it wants to kind of spread the beam out. And if the beam spreads out, the less you can actually focus eventually to the patient. So you usually use quadrupoles then to refocus that beam. If you shrink your synchrotron, make it as small as possible, you just don't have as much space to now have these quadrupoles and everything else then to refocus. So these bending magnets, these dipoles, they have to be properly tuned and manufactured, machined, so they can act both as a dipole and a quadrupole, so they can actually focus the beam for you as well. So again, anytime you make, the advantage of making something smaller, there's some disadvantages. Makes the engineering and the accelerator physics part just that much more difficult. But it's, as long as you take care of it and think about it ahead of time, you can deal with that. Right, then you have the accelerator portions to bring the beam in. Right here, the yellow part there is your radio frequency accelerator. So it basically has an electric field that goes back and forth, and every time the particles come in bunches. They are going around in a bunch, kind of all together, and when they hit this, they get accelerated, and then they're going around, and then they got accelerated. The magnets all change their magnetic field, and the accelerator changes its frequency a bit up, and then it comes back around, and each time it comes back faster, 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 so as they get more and more energies. Hence the synchrotron. So both the magnetic field and the RF are synchronized together to keep things moving. And they go around till you extract them. The extraction is also every part is very important, but understanding how the things are extracted in the synchrotron. And I'm spending a lot of time on synchrotrons because that seems to be initially the vendor that may go with is a synchrotron base. So it's good to understand these things. As the beam's extracted, I'll spend a little bit of time here for those that are more on let's say in the accelerator physics side, since we're at this center right now and not necessarily a medical physics center. As you know, if a beam's going around, you're going to extract, and the way you extract, for a synchrotron, you don't extract all the beam at one time. You extract the parts that you need, right? You need a certain amount because you're going to do scanning and so forth. So let's say a little bit older way of doing this is the beam would be on and off, one spot on, one spot off, and you'd move it. And as you can imagine, as you try to extract and not extract, not extract, it perturbs the beam a lot. And the more you perturb the beam, the more likely you're going to lose beam within the synchrotron. And then there's less amount of protons you have to treat the patient, and you have to refill it up, etc. So making sure that your extraction process is as clean as possible doesn't perturb the internal beam, so that you could keep that conservation very well, keep the large number of particles there to use to treat the patient. The second part on this extraction, I think, didn't have it on this slide. The second part of the extraction is, let's say, older systems or older methodologies, particularly for proton therapy, when you do a synchrotron base, do something that was called single energy extraction. I mean, you'd accelerate the particles to the energy you want to treat, and was mentioned before, so I kind of skipped it in the initial one. The energy is proportional to the depth in the patient, right? And that's the Bragg peak. That's the most important thing, and nothing goes beyond that one. So when you want a particular depth to treat that patient with, you do that by saying, I want a certain energy. And then not everything is that exact depth. So you need many, many energies to be able to treat and cover that tumor. So in a synchrotron, the way it was done before is you'd have single energy extraction, meaning you get that one energy, you treat that one energy, and then any protons you had left over in your accelerator, you had to dump them, refill it up, re-accelerate them to the next energy level, and then treat. That was single energy extraction. Modern synchrotrons do multi-energy extraction. That means you treat with that one energy, but then you don't dump the beam. You kind of use the synchrotron in reverse. Now you deaccelerate slightly. So instead of accelerating, now you deaccelerate that beam a little bit to the next energy you want, and then you extract. And that way, again, if your injecting system, that admittance and acceptance is well tuned, you're able to hold a lot of particles. And you don't need all those particles for one energy layer. You need them for several energy layers. So you're able to actually efficiently use everything you've injected. And then finally you run out and then you re-inject and do the next system. So understanding that whole process and seeing how efficient and depending how the extraction is done, when you extract, if you do have a multi-energy system, if you extract, and let's say you extract poorly, in not a very, in not the cleanest way possible, it messes up the beam. So then you can't, or it's very inefficient to go down to the next energy layer. You'll end up losing a lot of the beam. So taking all those into account to get a very efficient treatment, which is very crucial, as was mentioned. I think it was mentioned that I'll even say a low estimate is maybe 7,000 patients per year in Thailand that would benefit from proton therapy. And right now with the one room, maybe you're doing 350. So you need 20 of those at least, probably more. Well, one way is to build more centers, which is always a good thing. But the second way is also to make every center as efficient as possible. So that's why having that efficiency is very key. Because if you can actually treat twice as many patients in that same amount of time, well, then that's less of these centers you have to build. All right, so some ballpark numbers. So in general, protons are in the ring for the order of seconds. So a typical system may take a couple seconds to accelerate them up. They make several million revolutions going around there. So that's, maybe 1 or 2 times, depending how many are around the Earth, depending which one you're doing. And I said we treat with these energy layers. So you need, a few billion protons to do an energy layer. And you have, depending how you're doing these, you can have 100 energy layers or so per treatment. And then we treat many fractions, 10 or 20. I think the average was saying here in Bangkok for the proton center, they're doing average about 10 fractions. So maybe in all, to treat a patient, you're going to use a few trillion protons. Sounds a lot, but then when you really think about that, that's less than the number of protons in a nanogram of water. And if you picture a nanogram, I don't know. And I don't know how else to explain a nanogram, right? 1 gram is 1 drop. So cut that into 10 to the -9 versions and you have a nanogram. I put this up there because when we were treating with protons, both when I was at St. Jude and then at Mayo Clinic in Minnesota, before I moved to Mayo Clinic in Florida, we're building the Carbon Center. Patients would ask, like, what happens to all these protons? You're treating me with proton therapy, to kill a cancer. Your cancer is this big. You're killing that cancer. Where do all those protons go? And to be able to kind of explain to them that there's actually not that many protons that are actually going in. So when you think about it that way, it's really amazing that you could actually cure that tumor that little bit amount of radiation. Okay, so that was synchrotrons. The other accelerator that's used a lot to treat patients, and I know it's lunchtime, right? Everybody's hungry. I'm hungry too. Is cyclotrons. So here's really quickly, the Nobel Prize was awarded for the synchrotron discovery. This is very low. I think this is a few keV. But anyways, that was the first synchrotron, and here's one for particle therapy. So mentioned before, the basic concept. Maybe I'll just describe it, then turn around and try to describe it. So the cyclotron goes around in a spiral. There's these D magnets, so that would be fixed. The magnetic field would be fixed, and actually the frequency, the electric field, kind of in that gap. So the yellow is the magnetic field, and then in the gap is an electric field, and particles spiral around, get more and more. And as they get more and more energy, the magnetic field, since it's fixed, they make a bigger and bigger orbit, and then finally it's extracted. On the right is a kind of a modern one. Here there's the 3D, so you can see it has RF 1, 2, and 3. That's now the RF cavity. And the Ds don't actually look like Ds. They have this, I think, very interesting shape. And mainly that's because now we're dealing with relativistic. So it's not as simple as before. Here's a picture again. This is the now if you see how it looked here, the RF cavities and the D and the gap. Now you see them there, so now you can see okay, this is what it looks like. Um, Here's a typical cyclotron facility. Kind of similar. There's a beam line with the treatment areas and such. So you don't really have the injector that you would have for a synchrotron. You do have the source, but since it's very low energy, the magnetic field is able to move it around, and you could start with a very low energy, and it goes into the cyclotron. The cyclotron is on average smaller than the synchrotrons, but the disadvantage, you need the energy selection system. And I'll show that in a bit. But then you have your beam line in your treatment rooms. So here's one, it's 220 tons. The one you was here in Bangkok is physically smaller, same energy it could go to, but it's superconducting, it's physically smaller. There's the energy selection system. Again, not needed in synchrotrons. So it was mentioned, and when we talk about the shielding a bit, and I'll focus on a synchrotron system shielding, but you needed like 5 meter thick walls. I'll talk about that in the shielding aspect a little bit because I'll have some comments, but I won't save it till then. But the reason you need thicker walls for a cyclotron system is you only get one energy out, 250 MeV or 230 MeV. But generally, and you think a lot of the patients we talked a lot here was going to be a liver, pediatrics, small, so lower energy. Liver isn't really that high energy. In one of the talks, I talked about why people started with such a high energy. But you need to degrade that. So you get these very high energy, 250 MeV coming out, but you need 100 to treat the patient, 100 MeV. Well, what do you do with all that? In this type of a system, you need to go through a degrader. And basically, big hunk of plastic that just slows the beam down. And that creates a lot of neutrons, a lot of radiation waste. Here's the system, the degrader kind of coming through like this to kind of get the different energies that you want. So here, let me see. This, we'll talk about this portion right here. So that's the degrader with the kind of fingers to get the different, but the bottom graph's the important one. So again, out comes 250 MeV from the accelerator. This is log scale. So 100 corresponds to about 9 cm, 8 cm depth. Okay, so brain, right? You only get 1% of the beam. You throw away 99% of the protons that come out of the cyclotron. That's why you need these 5 meter wall thick things, because you're just throwing a bunch of stuff away and then you go through. So anyways, that's the main thing about cyclotrons. Okay, here's the Bragg peak. Since it's already lunchtime, I'll talk about this a little bit before. But basically, as the protons are going through, let's just say water for now, you lose about 1% per centimeter. So the number of particles go down, but their stopping power go up. So the amount of energy they give off per interaction. And that gives you your Bragg peak. So we already talked about the photon one, proton Bragg peak. Put them all together, you get a spread out Bragg peak. Carbons are a little bit tighter. But I talked about this more in some other lectures, so I'll go through fairly quickly since we're late. You have to measure these in order to put in your treatment planning system. This is a double scatter system and putting them together. So that's the old method. You get a lot of extra radiation. The new method, scanning, very precise. So difference, cheaper versus scatter. Scanning, more efficient. Spot sizes are important. And I talked about this in the planning. So measurement, I talked about this in the measuring portion. So the takeaways, so scanning beams are more efficient, essentially. And then for lunchtime, so I want to take any questions. Thank you. And I'll stand up to take questions. And I can also take them after lunch since I know it's lunchtime and we have a short lunch break. So.
Thank you very much for your presentation. I have a quick questions. Because different vendors use different accelerator system. Which part of the accelerator do we need to consider when we choose a vendor?
Okay, so the part of the accelerator, the key, honestly, I don't think the accelerator itself is that important. I think what comes out, the main thing is the overall efficiency of the system. So I wouldn't look at it and say, oh, is a synchrotron system better than a cyclotron system? They have pluses and minuses. I think at the end, it's really how efficiently can the whole system treat the patient. Once you decide on the system, like if, I know I wouldn't think of it as deciding on a synchrotron or a cyclotron system. You decide on a particular vendor because of everything they can offer as a package. After that, when you're now talking about shielding and different things, now you have to think about the important parts of the how you do those portions and how you're going to do the maintenance, et cetera, these different things. But I think the main part, and we talk about this a little bit later, is really how efficient, and we talk about uptime, et cetera, all these other things, how efficiently can you treat the patient? Because at the end, that's the main thing, right? You know, effectively treat the patient, but again, be able to treat many patients, because if you can only treat one patient an hour, that's no good, right? So I don't think it's really about that portion of how you actually are doing the accelerating. That becomes important, again, after you've decided on everything and you have to do the radiation shielding, you have to do the radiation safety, you have to think about the operation and maintenance, everything else, then it becomes important. But I would not make a decision of cyclotron versus synchrotron as far as the key thing deciding what I would do for patient treatment.
Thank you very much.
And what is your opinion about the compact and ultra compact proton? What do they use and how
Yeah.
the
Yeah, so
efficiency?
so
Because it's much cheaper and require much less space, though.
Yeah, so the trend obviously is I would say not even compact. The trend is to make things more just cheaper, less expensive, right? One way to do that is even the technology making it more compact isn't necessarily cheaper, but then the building itself becomes less, everything else becomes. So I think as long as making it compact is not at the expense of the quality of treatment. So some that I have seen in some proposals, they're making them compact, but then when you look at it, the quality of the treatment is being compromised. And I kind of skipped over a little bit quick there, but I'll just go back to this one right here. So I'll talk about this in the treatment planning portion a bit, but the spot size, and this is when you're treating. So you could think when you're treating with a beam, right? And it has a physical size to it. Well, the smaller that is, the more precise you could be. And obviously that's what we're interested in. We're just talking about 2 or 3 millimeters being precise so that we could spare normal tissues, et cetera. And if by making it compact, what you've given up is instead of having a small spot, now have a big spot. Well, is that really a benefit for the patient, right? Because now I've seen plans with some of the systems where they have a fairly large spot, and I could actually get a better plan with a photon treatment. Because just because it's a particle, just because proton doesn't mean it's magic, right? There's still the technique that goes into treating the patient. So those are the things that I'd be concerned about with some of the compact systems. The let's say the more traditional one-room system, like the Varian one-room system here, that's all. What that is they took their 3 or 4 room system and just selling it as a one solution. That keeps the spot size actually slightly bigger, but it keeps a nice, relatively small spot size. The dose rate is relatively high. So that's a good way to do one room system. I've seen other concepts where people want to do a one room system and they don't really say that, but what ends up being compromised are 2 things. The average dose rate gets low, and then the spot size gets big. So those are the things and you can make a compact system where you don't compromise that, but some of the systems that I've seen, that's where they end up compromising. So it's a it's a give and take there.
So you need a big size to get a smaller spots.
No, you need a well-designed system. So you could have a compact system with a high dose rate and a small spot size, but just because it's compact doesn't mean they properly did, because you can make it compact like I won't say username, like the system that's installed here, you see that it's going directly, there's not a band in your degrade. So in a cyclotron system, you usually have your energy degrader, these plastic fingers, and that gets you from your 250 or 230 down to your 100 MeV. When you do that, you get a lot of mixture, right? There's a lot of things coming out of there. I'm going to say it's kind of a dirty beam that comes out. And then you saw in the traditional thing, you have this bend. Well, what that bend is actually the energy selection system. So after you go through this degrader, you go up from 250 to 100, but you have 100 now plus or minus like 7. So you have this kind of now in depth, this big beam, and also spread out. You just went through all these things. You no longer have a focused beam. So the traditional way is then to go through this energy degrader, this bend, because when you do this bend, you're able to set the magnetic field at a certain thing. So only the energy you want comes out. So now instead of having 100 MeV plus or minus 10, you have 100 MeV plus or minus 1. The plus or minus is important because that's the depth. But now when you go through the gantry and everything, that says how well you can squeeze the spot into make it a small spot. So if you don't, now you saw the system with the one room system, it comes kind of straight in. There's not that bend. So what you have to do, you have to design your gantry, because the gantry is a bend. You have to design the gantry so it could properly do an energy selection system and do the bending to treat the patient. So if you don't do that right, now you're having this one magnet kind of do dual purpose. And as long as you design it right, you could keep good energy selection. You could keep a relatively small spot size. If you don't do it right, if you don't put enough thought in it, and thought actually means expense in the design and everything, then you can't keep your small spot size and your good energy distribution. So that's what I'm saying. Just because you make it compact doesn't mean you necessarily give up those things. But if it's not something that was thought about, and when I say thought, what I really mean is engineering time. And what engineering time and design time means is cost to the vendor, right? They had to spend time and money to figure that out right. And if they didn't spend the time and money to figure it out right and just sell the system, basically it will still work, but you'll have a low dose rate in a big spot. So it depends how much effort they put in. The effort means cost and et cetera. So that's the kind of give and take there.
Right, thank you.
Yeah. Right. Thank you. It's already 12:20, so it's lunchtime.
Thank you, Professor Chris. This is all of the morning session. And we will have a lunch break for an hour and resume at 10:01. Your lunch is already prepared in the same room at your refreshment on your left-hand side. And you can take your lunch there and have it here in the meeting area. And after you come back, Professor Chris will take the lead for other section according to the agenda. Thank you.